Namaste and welcome back to the course on statistical mechanics of phases and phase transitions. We are now visiting the chapter on non-perturbative approximate methods. We have discussed the Feynman variational principle and we have formulated the framework for doing mean field theory. So briefly, Feynman variation principle will find a proxy Hamiltonian which has some set of parameters which will optimize to give a bound on the free energy, and from there you will use the proxy Hamiltonian to study the physics of your problem. So the Feynman variational principle, when you apply to say the Ising model, will show that there is symmetry breaking in all dimensions. It does help you get to some critical experiments, etc., but they do not match experiments. And we went on to look at a different formulation, a different method to approximately solve problems in the non-perturbative regime, and this is mean field theory. And what we have seen in the last lecture was the formulation of mean field theory. And mean field theory, as we just discussed in the last lecture, involves viewing the Hamiltonian as products of fluctuating terms and replacing this product by a fluctuating term seeing the mean field of the other term, etc. And then finally we will set up a set of self-consistency conditions that will solve for the mean fields, the unknown mean fields of our problem. So we will in this lecture apply mean field theory to the cubic lattice Ising model in d dimensions. Okay. So let us just revise the formulation of mean field theory. So the Hamiltonian is defined over a set of configurations, and this Hamiltonian is formally in this general framework is viewed as a sum of terms involving product of fluctuating terms. So A is a fluctuating term, meaning that in the thermal ensemble A will take on different values, and B is also a fluctuating quantity. And from here, by using the mean field approximation, by thinking of this A as a sum of a mean field plus a fluctuating term and ignoring the correlations between fluctuations of A and B, we were able to write down the mean field Hamiltonian. And a crucial further approximation we made was that the mean field values are going to be evaluated in the same mean field Hamiltonian. And what you will, to do this, you will end up getting a set of self-consistency equations. So what I mean by that is, suppose you assume that these values are there, mean field of B, mean field of A, suppose someone gave you those values, you can compute the partition function and you can compute the probability distribution, and from there you can extract back what are the expectation values of this. And so the important statement we are making is that this, what you put in should be what you should get out. If you do not, you have to readjust the parameters and find the solution of those equations, and that will set up what is the mean field Hamiltonian for you. Okay. So this is the mean field theory that we discussed in a general setting. I discussed it in a general setting particularly because in case you want to do it, use this in your own research, then of course you can take the particular Hamiltonian that you have zeroed in on, and then you can look at the terms in that and use this formalism, and hopefully you will be able to make some progress there. Okay. So now let us see how we will apply this to the d-dimensional cubic lattice Ising model. So I start with d cubic lattice where I have n sites, and they are as usual written as L tilde to the power d, and the sites are labeled by this capital I. So in this discussion I am going to have the Ising interaction with the exchange coupling over nearest neighbors I and j, and I am also going to hold on to an external field that I am applying. And you will see why I am doing this in a bit. So the coupling constants here are the exchange constant, this J, this H, and of course the temperature, and from these you can construct variety of dimensionless coupling constants. Okay. So how do I think about the mean field theory in this context. So, if I look at this term, the magnetic field term, I do not have to do anything about that, because that is just a set of a sum of terms, each of them is not interacting with anything else. So, if I had just that piece, I can solve the problem, but this one is the one that I have to deal with. So, now you see we had this alpha, which is a set of some index labeling the terms in my Hamiltonian. So, in this case that alpha turns out to be the links of the Hamiltonian, links like this, right. So, what I am going to do is I am going to look at a link and I am going to take the term associated with that link. So, that is Si and Sj. The spin at site I is a fluctuating quantity and the spin at j is also a fluctuating quantity. So, what am I going to do? I am going to make the mean field approximation for that. And what is the approximation? I am going to replace the Sj term by its mean value in the mean field ensemble. So, Si now, which is fluctuating, sees only the mean field of the or the average value of the spin at j, and this is, and vice versa, j sees only the average value of the spin at I, and as we noted in the last lecture, we have to subtract out this product of this means to remove double counting of the expectation values. Okay. So, this is what I start off with. Now, what I am going to do? I am going to take this expression and I am going to write the mean field Hamiltonian using taking this and sticking it into this terms and working with the resulting math. Okay. So, let us see what happens. First, let me tell you about the easy terms. So, when I look at this term, for example, product Si mean field Sj mean field, when I put that in this expression, this minus sign will cancel this minus sign. So, I will get plus j times the product of mean fields on each individual links. So, this should be links, this should be less than greater than, it should be a link here. Okay. So, it is not I comma j, it is on links. Okay. What happens to these terms? Now, these terms, if I look at the site I, the site I that is sitting here, so I am showing here, I am labeling the site here by 0, it is seeing 4 neighbors, 1, 2, 3, 4. Each of those neighbors, they are going to give me a field, something like a field, which is the exchange constant times the expectation value of the on mean field, that is this term. So, j is equal to 1 here, it will give me that. And what do I have to do? I have to look around and find out all the neighbors who are coupled to me. And so, what I have to do is I have to sum over the mean field of those, or the mean value of Sj of all the j's that are neighbors of I, correct, and multiply this by j. I am assuming j is same on all links, so it is a clean problem with translational symmetry and so on, right. It is a simple problem that we have set up here, and so you can now view this quantity as an effective molecular field. Okay. So, this word molecular field was introduced I believe by Bragg and Williams when they introduced these ideas quite a while back. Okay. So, this is the field seen by this spin at site 0 in the picture that I am showing here, coming from the neighboring spins. Okay. All right. So, what do we have here? We have this effective molecular field which is being seen while it is sitting in this lattice. There is the external field, we are not touching that term, but that is just coming for the ride, we have not done anything with it, I mean it is just there. And then there is this term which is a set of numbers, remember we do not know what these numbers are yet. Okay. So, what we have done is we have reduced the problem to isolated spins, each of which are seeing an effective molecular field. At this stage we do not know what those molecular fields are, right. Okay. All right. So, now First thing to note is that how many unknown parameters do we have? So we said that each link has to be broken up into the product of the mean fields and so on. So you will see that there are as many unknown parameters, namely expectation value of Si for all I belong to all the sites. So there are as many unknown parameters in this story as there are number of sites. So this might scare you away because you might think, well, how am I going to, if I have 10 to the 26 sites, how am I going to deal with this? Or why 10 to the 26? If I have 100 sites, that will be a problem, right? So now we have to appeal to physics. So you realize that if I choose these numbers differently at different sites, that means I am breaking translational symmetry. Remember, these are expectation value over some ensemble. So if I get different expectation value at different sites, that means I am breaking translational symmetry. But I know from experiments, for example, that the magnetization is same quote unquote everywhere in the crystal. So if I take a sample, it's the same, if I look at this region of the sample, that region of the sample is the same everywhere. So what we are going to say is that, okay, I am looking for a mean field which is translationally symmetric. So when I do that, I have to now enforce translational symmetry on these mean fields, which will force every one of these terms to be equal. So I am going to make an ansatz which says that the expectation value of Si is independent of I and is equal to some number m. And this, if this turns out to be non-zero after I find self-consistently the value of this, then it's breaking the Z2 symmetry of the Ising model, because of course if this object picks up an expectation value, we know very well now that you are breaking symmetry. But we certainly do not allow for breaking of translational symmetry within this framework that we are discussing. Okay, so that is a great deal of progress, because with this framework I can immediately simplify the mean field Hamiltonian I wrote down in the previous slide, namely this one, into something that looks much more human readable. So what is this? So you see, since the expectation value of Si is independent of I, the effective molecular field will be the exchange coupling times the number of nearest neighbors times the expectation value of S. But the number of nearest neighbors in a d-dimensional cubic lattice is 2 times d. So this is where the dimension of the space will enter our mean field theory. Okay? Alright. And then this H is simply the external magnetic field that you have applied. That just comes to the right, we are not touching that. Okay, so that is the explanation of this term. What about this term? So you see, that term was sum over all links. So remember, there is a typo, that is over all links. How many links are there? There are d times n links in a d-dimensional cubic lattice with periodic boundary conditions. And each of this will give me m square, and that is exactly the term that we have here. D times n, number of links, J is the exchange coupling, times m square. Okay, that is very simple, and what you will now see is that we have to impose self-consistency condition. But the self-consistency condition is now very simple to impose, because we can solve, as we did in the lecture on Feynman variational principle. These are a set of uncoupled spins now, so you can simply solve the problem of a single spin, and you know that a single spin in a magnetic field, its magnetization, namely the expectation value of this the spin operator, will be just the tan h of the effective magnetic field divided by temperature. Okay? So this is a very nice result, in the sense that we have now extracted the self-consistency relation, and mind you, this looks exactly like what we found in the Feynman variational method. Okay? Alright. Suppose I solve this equation, I will find some value of m which satisfies the self consistency condition, and if I take that value of m and put it in this expression for the free energy, then I will get a free energy density. Now I get a free energy density because everything will be proportional to n correctly extensive, and I can divide it off and I will get a free energy density, which is this. But for this I have to stick into this term the value corresponding to the solution of this self consistency equation. Okay. So let us explore a little bit about the self consistent solution of m. We have discussed this when we were discussing the Feynman variational principle. Let us go through this again very quickly. Suppose I were to focus on the case where H is equal to 0, then you will see immediately that there is a natural energy scale in the problem. You can already see that here. There is 2dJ sitting here. That is a very natural energy scale in the problem. That energy scale will determine the Tc. So what do you mean by saying that it will determine Tc? So if I try to solve that equation m is equal to tan h of blah blah, then I will find that there is no solution other than m equal to 0 when t is greater than Tc. So the slope of this tan h curve will be less than 1 when t is greater than Tc. You can see that the slope is inversely proportional to the temperature. So the critical temperature occurs when the slope of this tan h at m equal to 0 is equal to 1, and that is where this tan h curve will be grazing this this straight line here with slope 1, and if t is less than Tc, then you will have two solutions. Now it is very nice that it has two solutions because it is telling you that you have a broken symmetry, and mind you, the magnitudes of these solutions will be always equal. Okay. So when t is less than Tc, you will have two solutions for m. There is also a solution at 0, but that will, if you put it in the free energy, you will find that that solution has higher free energy. So you can safely discard that. So now comes a very nice result. So you see that the solution of m is already an order parameter, and this is what I had advertised the advantage of mean field theory. So you do not have to do any further thinking because your mean field was already an order parameter. So now you have realized that when t is less than Tc, you have this non-zero order parameter and you have broken symmetry, and in a sense you have found the phase diagram in the temperature axis, if you wish. So above Tc you have this paramagnetic phase, and below Tc you have this ferromagnetic phase. Okay, what else can we find? So you can see that result that we have there in the previous slide is something that we already had found using the Feynman variational principle. So now what I am going to do is, I am going to ask what happens to the Ising model if I have an external magnetic field which now breaks Z2 symmetry. Okay. What this mean field theory allows you to do is you can also solve for this mean field m, the self consistent mean field, in the presence of the magnetic field, and that self consistent solution will change when you change the magnetic field. So what we are going to look at in this slide is we are going to see what is the phase diagram in the TH plane, right. So this is done numerically. For arbitrary value of t and h, you can do it numerically. Okay. So I have made a plot of this. So let me just walk you through this graph. So this axis here is t by Tc. It starts at 0 and goes all the way to 2. This axis here is h by Tc, remember H in the way we discuss things has dimensions of energy. Magnetic field in the way we set up the problems has dimensions of energy. So H by Tc is a dimensionless number, and you see this line here going that way, that is the line where H is equal to 0. Now you see when H is equal to 0, below T by Tc equal to 1, namely T less than Tc, you will see that as you approach H0 from either side, you have two distinct solutions, the positive solution and the negative solution. Okay? And the main observation here is that if I turn on H, keep H fixed, turn it on and run temperature, you will find that there is no phase transition when H is non-zero. So that is, if you start somewhere here, it will sort of smoothly go, the magnetization will smoothly increase and it will go all the way to 1 as T goes to 0. There will not be this sudden change of, this order parameter will not have this non-analytic behavior. It will be perfectly analytic all the way if you are working at a fixed H and changing the temperature. So what is this telling you? This is telling you that if I want to access this critical point, I have to fix two parameters, namely I have to fix the temperature and the magnetic field. So the temperature has to be equal to Tc and the magnetic field has to be 0 for me to see this critical point. If I have a magnetic field, I will not see any phase transition. Okay, this is a very important observation, as you will see. Second, imagine I have a state where I have magnetized in the positive sense here, right, so where I am pointing to in this region. And in this regime, I have something which is negative, magnetization is negative. Now suppose you had all the required experimental facilities. The point is, I can go from the down polarized state to the up polarized state without encountering any phase transition. How do I do that? I just go uphill here. So what I do is I keep the magnetic field on, turn on temperature, go to high temperature, then I turn the magnetic field on in the other direction, I turn it off, I go to 0 and then I turn it on, again go positive to some value, and then I reach here and I cool it back. You see, so I can go from this way all the way to that way without encountering any phase transition. Okay? So this is an important observation, as you will see. But you can ask a different question. Suppose I am at some low temperatures, so I am at T less than Tc, and I try to change the magnetic field from negative to positive. Then I will encounter a discontinuous jump in the magnetization if you allow for sufficient equilibration, etc. You will end up getting a first order transition. So if you go this way along the in this phase plane, that is, if you keep temperature fixed and say start from a negative magnetic field and go all the way up to some positive magnetic field, then at the 0 magnetic field you have a first order change. You will change from everything polarized down to everything polarized up. Of course, you have to do this carefully, and otherwise you can get hysteresis and all that. But if you do this carefully enough, if you give enough time for equilibration, you will see that there is a first order change. Okay, why did I make a big deal out of this? So now if I look at this, I am looking at the same plot that I have here, but I am now looking at it as a contour plot of the magnetization. So how do I look at this phase diagram? The phase diagram is that this is the H is equal to 0 line. That line here is a line of first order transitions. You see, so this is the first order transition when I am temperature, let us say 0.5, if I am at negative H, I start increasing H to positive values, I will encounter a first order transition and go into this up polarized state. From down polarized state, I will go to the up polarized state. And you see, I can, if I did not want to encounter this first order transition, I can go up in temperature at negative magnetic field, then increase my magnetic field to positive value, and then reduce temperature down to 0, and I need not encounter this first order transition. Now the question is, have you seen this before? And the answer is absolutely yes. And that is in the liquid gas phase diagram. So in a sense, this picture is quite similar to this picture. You see, there is a line of first order transitions, and there is a line of first order transition, and it ends in a critical point. Exactly here, the line of first order transition ends in the critical point. You have magnetization up here and down here. You have one kind of density here, low density here, and high density there, and you can see that it is very similar. Similarly, gas and liquid are not distinguished by symmetry, right? We have discussed this, and therefore what I can do is I can go around, if I have the experimental facility, I can go around this critical point by changing my, so for example, I could keep the pressure fixed, increase temperature, then increase the pressure, and then reduce the temperature, and that is exactly what is happening also in the Ising model. So this pressure here is like a magnetic field, right? Of course, it is not literally the magnetic field, but so in some sense, you know, this if you were to take a line like this, and you can make some dimensionless quantity that is parallel to this line, that will be like the temperature of this problem, and whatever is the orthogonal coordinate of that, that will be like the magnetic field of this problem. So in this vicinity of this critical point of the liquid gas, this problem is quite similar to the problem of the Ising model. So now we are beginning to see the contours of understanding how this kind of universal physics is going to emerge. We are already seeing that the structure of the phase diagram and the type of things that are going around in these different, very different systems. You see, these are the atoms and molecules and so on. This is spins on a lattice, and yet they produce this kind of very similar phase diagram, etc. Okay. So let me continue. So we can extract a lot more juice out of this mean field theory, but before that I mentioned some striking similarities between them, between these systems, but you must also note that there are some crucial differences, right, and I urge you to sort of look at those differences. Okay, let us proceed. Now what we are going to do is, we are going to take this mean field theory and we are going to analyze the mean field theory near the critical point, and we are going to, our goal is to try and extract some critical properties. We want to extract for example critical exponents. Okay. So as always, whenever we want to extract critical exponents, we will look for some kind of dimensionless parameter that tells us how far away we are from the transition. So the natural candidate in this context, which we have also seen in previous lectures, is this little t, which is the temperature minus Tc divided by Tc. Okay. So to proceed with the analysis, and let me give you a brief idea of how this analysis is going to be done so that you can take your pen and paper out and just work this out for yourself. We are going to be near the critical point. So what that means is the magnitude of little t is going to be much smaller than 1. That is what we mean by being near critical point. Remember now, to set the critical point, I had to also make sure that h is 0. Right? If h is not 0, there is no critical point. Okay? So I have to make sure that mod h by Tc, remember H has dimensions of energy, mod H by Tc is much smaller than 1. So that is what will define the vicinity of the critical point. So I can just, so I am sort of here in this regime, right, and that is the vicinity of the critical point. So if you agree to be in this regime, then all the quantities that we are interested in, namely the magnetization and the magnetic field, all of those quantities are small. Remember, I am not saying any coupling constant is small, I am saying that some quantity which comes out as an expectation value of some observable is small. And of course, the coupling constant H is small because I want to be near Tc. Okay, there what you can do is this tanh function, hyperbolic tan function, it has an expansion x minus x cube by 3. It is an odd function, so it has only odd powers of x, of course. And so what I am going to do is I am going to take this m and replace it by the linear term here plus the cubic term with a factor of 1 by 3. If I do this, you will see that it will gain me a lot of mileage. Okay, so first things first. So now suppose I put H is equal to 0, you will see that this equation will tell me that m is equal to m multiplied by Tc by T minus 1/3 m cubed multiplied by Tc by T. So you see, if I am looking for the non-zero solution of m, then when T is less than Tc, this will have a non-zero solution of m, and you can see that that solution will be will give you a solution for m square. Naturally it has to give you a solution for m square because the original problem has Ising symmetry. So if I have a solution at plus m, there should be a solution at minus m, because if I have a symmetry, then the state that I get by performing the symmetry operation should have the same energy. And in the absence of H, when I have that symmetry, I will see that the solution for m will depend, m square will depend linearly on T when T is less than 0. So m will go as square root of distance from transition when T is less than 0, and of course 0 when T is greater than 0. So this immediately tells us that the critical exponent of this theory, what this critical exponent is being predicted in this theory is 1/2, which is exactly what we found by the Feynman variational principle. And again you are finding that it is not dependent on the space dimension, and we know all the criticisms of the Feynman variational principle, so you can apply the same things here. But remember that when we did the van der Waals gas, we also looked at the difference of density of the liquid minus the density of the gas, and we had also defined there a distance to transition. We again found that that quantity also went as square root of the distance to transition, and therefore we also found beta is equal to 1/2 there. So now we are finding two very different systems, Ising spins and liquid gas, having the same critical exponent. Okay. All right, we can look at more properties. So we can look at the specific heat. We know that, I have showed you data before, we know that the specific heat diverges near a critical point. So let us see what happens here. So again, exploiting the fact that little t is a small quantity, I am going to use the solution of m. So I take the solution of m, which we just put it down in here, it is square root of 3 times mod t, and I can put that in this expression for free energy that we have here, in this expression for free energy, and perform a calculation keeping t small. So I do some simple expansion, which is very straightforward to do, if maybe a little tedious, but it can be done, right, and you will end up getting a term like this. So when t is less than 0, you will see that there will be only this term. When t is greater than 0, it will, this minus log 2 t term will be there. Okay. And when I explore what happens to the specific heat. So what I have to do is, specific heat is related to the derivative of some free energy. So in fact, you can show that the first derivative of the Helmholtz free energy with temperature will give you entropy with a, if you have a negative minus sign of that, and then you take T times T ds by dt will give you the specific heat, right. That is the heat divided by change of heat added to the system divided by infinitesimal temperature that you need to change that. And if so, I have to end up taking two derivatives of this function f with respect to little t, and that will give me the specific heat, and I have to put a negative signs to make sure that everything is okay. And you see that will give you a specific heat which is non-vanishing when you are below Tc, but vanishing when you are above Tc. Now you may wonder like what is this strange result? Well, that is what this theory gives us. It gives us that the specific heat has a jump discontinuity at the phase transition. This certainly does not agree with experiments on 3-dimensional magnets, etc. Right. So even in high dimensions it does not agree. We know that there is a divergence in specific heat, and what you end up getting within this theory is that you get a jump discontinuity in the specific heat. Okay. So we have looked at the critical properties associated with the order parameter associated with the specific heat. So let us push along and try to see whether we can study the magnetic susceptibility. So this is a very nice exercise for you to do. You should definitely work, I will show you some results, but you should definitely work these out. These are very instructive. So you see, in this system we already have developed a magnetization in at temperature T less than Tc. So you have to be very careful in analyzing the system when you are below Tc and you are above Tc, because in the above Tc there is no magnetization that is developed. So you can simply try to find the magnetization for an applied field and just divide off and so on. The main message I want to convey is that you have to look at the response of the magnetization, which is the change of the magnetization. This delta m is what you have to find. So above Tc, if you keep to lowest orders, you will see that the self-consistency equation will give you this. It will give you that delta m is equal to h plus Tc by T delta m, right. This is what you will end up getting. And this will immediately tell you that the susceptibility, so you can solve this equation and find delta m in terms of h, and then you can find the proportionality constant, and that proportionality constant is indeed the susceptibility. And that susceptibility, I am making it dimensionless by multiplying it by Tc, is 1 by T. So it is diverging as 1 by T. So this is very nice, right, and if you realize this is what is called as a Curie-Weiss law, it is diverging as 1 by T. But when T is less than Tc, I have to exercise some caution in the calculation because I already have a magnetization that is developed. And so the change of the magnetization from this order parameter on the application of the field, if you expand to linear order, you will end up getting something like this. And if you solve this equation, and remember m square goes as that 3 times mod T, etc., you will see that the susceptibility goes as 1 by 2 times mod T, in the sense that the divergence, the power law dependence on T is the same on both sides. So what we have shown is that there is singular behavior of the susceptibility, and the critical exponent gamma is 1, and remember we talked about these amplitude ratios. The ratios of the coefficients around if I take the ratios of that, it turns out to be 2 in this case, which is indeed a universal number, right. So this number is also a characteristic of the phase transition. Now of course we have pulled off a critical exponent from this calculation, but again I would draw your attention to the fact that when we worked out the van der Waals gas within the approximations that we made, we again found that gamma was equal to 1. So now we are seeing that there is a connection to the van der Waals gas as well. Okay, so you see I carefully sidestepped the question of what happens at t equal to 0 here. So this result is valid for t less than 0 and this result is valid for t greater than 0. What happens at t equal to 0? So the message I want to convey in this slide is that at t equal to 0, the system does not have linear response. That means if I keep the system at the critical temperature and apply magnetic field, the magnetization I will get will not be proportional to the magnetic field. It does not have linear response. How do I see that? If I take the self-consistency equation at Tc, okay, m is 0, so please ignore this parenthesis, that is a typo, right, you will end up getting an equation like this. So if you solve this equation to lowest keeping the correct order of terms etc., you will find that delta m goes as some number h by Tc to the power 1/3. So that means the magnetization grows as cube root of the magnetic field. That is how the magnetization goes. It does not go as proportional to h. This is what I mean by non-linear response. So this number 3 here is usually considered as a critical exponent, and that critical exponent in this theory turns out to be 3. Okay? Alright. So these are the things that we can extract from the mean field theory. And so if you look at what we have achieved here is we started off with the Ising model in d dimensions and we extracted the full phase diagram and the critical properties. So we have in a sense solved the problem in all regimes of T, H, J, everything. So you might think that this is a great step forward. It certainly is a step forward, I do not know about great, because it has problems. So for example, none of these exponents depend on space dimension. But we know that the exponents of the Ising system are dimension dependent. For example, we know the exact solution in 2 dimensions for beta, it is 1/8, and it is something between 0.3 and 0.35, 0.325 or something of that order in 3 dimensions. So we are not finding any dimension dependence in these mean field results. Second is we are finding that there is an ordered phase in d equal to 1, which is terrible, right? I mean, this is completely disastrous. We have not gotten any advantage over Feynman variation principle. In fact, you just see that what we have done is a different way of doing the Feynman variation principle without thinking about guessing a Hamiltonian, etc. The Hamiltonian simply came up by looking at the terms in in some sense the h lambda that we had to guess in the Feynman variation principle. Here we just got it by a systematic approximation to fluctuating terms and looking at mean fields, etc. So the critical exponents do not depend on d, and if you go back a couple of lectures, I had a long critique of the results of the Feynman variation principle. Whatever problems we listed out there, they are also applicable to this mean field theory. Okay? So that is the situation. So it is a good time to conclude this lecture, and let me tell you some advantages of mean field theory. So advantage of mean field theory is, you see, we were able to map out the phase diagram of the Ising model in a fairly straightforward and very simple way. We got wrong results in low dimensions, but our results are definitely good in, at least qualitatively good in 2 and 3 dimensions, etc. The great advantage of using mean field theory is that many of the mean fields, after you solve them, you do not have to think more about what you have found, etc., because they will turn out to be the order parameters that you are looking for, and whenever there is a regime of parameters in which those order parameters become non-zero, then you know that you have realized some phase or the other. the self-consistent equations are the central things here, and you have to solve them non-perturbatively. You have to solve, if you need to use numerics, you have to use numerics. So here is from the physics perspective, broader physics perspective of and the goal of this course, etc., in terms of understanding universality, etc., we have made some very interesting progress. We have found a deep connection between the phase diagrams of the Ising model, which is made of spins sitting on a lattice, to a system where there are atoms and molecules moving in the continuum. Our theories for these two things are built on completely different ingredients, right? Yet they have produced very same critical exponents for variety of quantities. So this must be encouraging to us. But we know that the critical exponents that we have extracted do not match experiments. So that is a bit of not a happy situation, but perhaps we should look at it as an opportunity to understand why we are different from the actual experiments. And the broad message, which is also coming in from the Feynman variational principle, etc., is that all these kind of approximation methods which ignore fluctuations or correlations between fluctuations of variety of quantities, they seem to do better in higher dimensions. So already we are getting a sense of the importance of fluctuations in lower spatial dimensions. Okay? So where are we going to go next? So what I would like to show you is, I would like to show you an example of a system where we start from some known experimental data. So somebody has done a set of experiments and they have mapped out some phase diagram, etc. I will try to show you an example where we start from some known phase diagram and we construct a model to get that phase diagram, analyze using mean field theory, and come up with a variety of phenomena that are observed and maybe some of the things that we can predict which the experimentalists can go and check. So I am sure that that should be very exciting for you, and I am even more sure that you will join us for the next lecture. So I will see you in the next lecture. Have a good day.